Yeah, you can start. I mean, what we're talking for the break, if I remember correctly.
Yep.
Break. Okay, it's late. We'll hear something about braids.
Thank you for the lengthy introduction. So I'm happy to be here and be able to talk about braids, which we have not seen a lot this week. So first, I'm gonna say what braids are. This is a joint work with Vincent Vugier, which is my supervisor. What are braids? So we can see them as 3D objects, as a collection of strands in the 3D space, more precisely as a continuous image of segments in the space. And we can see that they can intertwine themselves and have different positions relative to each other before arriving at their destination. And what we want to study is not their exact position, but the knots they form along the way with each other. So we're going to look at them up to continuous deformation. This has some application in quantum physics to study the particles, quantum particles, and how they intricate with each other. But I'm not really good with continuous stuff, so I really like to make everything discrete. So we're going to see braids as a sequence of elementary operations. So here below, we have the same braid, but at the top, you can see the middle strand going here and the same path here. And we can decompose it into a sequence of elementary operations, which are, for example, sigma 1, which is going to be the operation that swaps the first strands at the bottom with a second going up to above it. And for example, sigma 2 that swaps the second strands with the third going above. So this is nice and all. We can now work on those letters, on words on those letters, instead of working with topologic stuff. And my objective will be to study normal forms. But before introducing normal forms, I need to make what I said a bit formal. So we're going to start with a set of finite elementary operations with sigma I swapping the strand I with I plus 1. And I'm going to be working with words on this. But we still want to look at them up to continuous deformation. So how will that translate in the discrete case? So we'll have a set of relations which are going to inform us on whether braids words are equivalent up to deformation. So there's two kinds of relations. The first one are commutation relations, which are pretty self-explanatory. Some letters commute. And that's just when they don't involve common strands. And another class of relations are braid relations, which are specific to the monoid, and which corresponds to the fact that when swapping the strand 1 with the strand 3, there is two ways to do so. Either the strand 2 goes at the bottom or at the top. You can see that there is a continuous deformation from one to the other just by pulling the right strand up. Okay? So two words are going to be equivalent if there is a sequence of relations going from one word to the other. In that context, braids are going to be equivalent classes of words relative to those relations. So for example, I'm going to take any braid, any word, and I can see that I can apply some relations to find new words representing the same braid. So here we have a commutative relation, so I can commute. Here I see that there is a pattern where I can apply the braid relation. There we go, and so on and so forth. So all these words are representative of the same braid. You can observe that every relation conserves a number of letters, so every representative of the same braid will have the same length. Okay, but we want to have more structure on this because for now, braids are only equivalent classes of words. There is no structure here. So I'm going to take a smaller example to talk about what structure there lies behind. So here the braid beta has 4 representatives. They all fit on the screen, so this is nice. W1, W2, W3, W4, and we can go from one to the other via a sequence of relations. Okay? So nothing new here, but I'm going to represent beta as a DAG with some relations just to have some more compact information about beta. So here we have beta on top, which is our braid, and at the bottom we have a node representing the empty braid, the trivial braid, and every node corresponds to a braid along the way. Each arrow is a letter, so each path represents a word. And what's nice is that we can recover every word just by reading the path from the bottom to the top. So in this context, cells represent relations because there are two different ways to obtain the same braid. So here we can see that we can read the W1 at the leftmost path and apply relations to get every single representative. Okay, but we can do more than this with this representation. In particular, we can define what are left divisors. So every node here can be completed into beta. So we'll say that they are left divisors because they are kind of a prefix of beta. So for example, here, sigma 2, sigma 1 can be completed into a full braid beta. And this gives us a lattice structure on braids, which means that we have GCD and LCM relative to this divisibility relation, which is nice because it allows us to do a lot of things. And there is one kind of divisors that I'm really interested in is divisors of length 1. So this is all the letters with which we can begin writing beta with. So I'm going to give a name to that. This is L of beta. The left of beta is the set of letters with which we can begin writing beta. So here we have only sigma 1 and sigma 2. Okay, this will become useful later. Now I can discuss what normal forms are. It's simply a way to choose for every braid a single word representing it. So we want to do this because if you want to do some computation on braids, for example, just to compare braids, it's nice to have a single representative that's going to tell us, okay, if these representatives are equal, then the braids are equal. Otherwise, manipulating braids in a computer is not really feasible. And the problem here is that we have no canonical way to do it. Every choice seems reasonable at first. So, I mean, we're going to try some things and hope that those languages have nice properties. So let's go for it. One thing we can define is the lexicographic normal form. This is maybe the most natural one, which consists of choosing the minimal representant in lexicographic order. What I mean by that is that each time I have a choice when writing a letter, I want to take the minimal letter, the minimal index. So for example, here for beta, at the start, I see that I can choose between sigma 2 and sigma 1. This is defined by the left. And so I choose sigma 1. Here I have another choice. I choose sigma 1, and so on and so forth. This defines a unique representative. And this has been studied pretty extensively. It has nice properties, but not everything we could wish for. So I'm studying another normal form, which is the alternating normal form, which has linked to a lot of things in braid theory. And the idea here is to consider the largest prefix of beta, the largest left divisor that doesn't use a specific strand, here the top one. So this is all we can do without using sigma n minus 1. After doing that, we're left with probably something else. And we're going to define beta 1 as the largest prefix, not using the letter sigma 1, and so on and so forth. This is not yet a normal form because each braid has still a lot of representative that can be used. So we're going to do that recursively, decompose each block recursively with the same method until we arrive at 2 strands, in which case we have only one choice for every braid. So let's do it on an example. So I'm saying that beta here is an alternative normal form for 4 strands. So how do we observe that? Well, first we find the decomposition. Here, we do not choose the top strand. Here, the bottom is the top. Everything's fine. But also, we need to check that each block is maximal, which means that we need to check that there is no other representation of beta that has a bigger first block. To check that, we'll use the notion of left. We check that the left of the rest of the braid doesn't have anything else that's sigma free. If it has something else that we could put at the left here via rewriting, then the first block would be greater. So this is the only condition we need to check that the first block is maximal. Then for the second, we do the same, and so on. And we also need to check recursively that each block is put into recursive normal form. Okay. One thing to note here is that the left of beta is computable, or else it would be kind of annoying. We can compute the left from pretty easily by reading the word from right to left. So that's okay. So I've said that, but I've not said what makes a good normal form. So we're going to discuss about that. A good normal form is a normal form for which it's easy to check whether a word is in it. If we cannot even do that, it's kind of pointless to have a normal form where we cannot do anything with. This will be linked to the notion of regularity, so being recognized by a finite automaton. And in a perfect world, the minimal automaton recognizing this language would be small. Another thing we would want our normal form to do is for it to be easy to compute the normal form of a word, of any braid from any word. So we start with any word and we want to find its representative. It's actually much more complicated than the first one in practice, and this is linked to automaticity. So here I'm only going to talk about this. So this is the main subject of my thesis, but I don't have time for everything. So here we go. I'm going to talk about the regularity for normal forms. Okay, so I'm going to do a very quick summary of what are automaton, because I think most people are familiar with. So we have a set of states, a set of transition with labels on them. Here, all our states are accepting because all our languages are closed by prefix. And a word would be recognized by an automaton if and only if there is a path that produces that word when going through it. So for example, here I'm starting with a word on letters in the braid monoid, and I'm gonna see if it stays in the automaton. So you can just do a little walk around the automaton and find out that, yes, indeed, this word is recognized by our automaton. Notice that here, if I read a sigma 2, I would go out and I won't be able to read it. Okay, so what is the language? What is the set of all words recognized by this automaton? Well, actually, it's all the words in alternating normal form with 3 strands, and also all the words in lexicographic normal form with 3 strands. So they coincide for 3 strands. This is not true in general, but there's not much happening in 3 strands, so they do coincide. And this is actually a general result. What I mean by that is that the lexicographic and the alternating normal form are both regular for every n, which is nice, which is why we keep studying them, because else we won't study them, probably. Okay, so this is cool, but the construction of the automaton for the alternating normal form gives no explicit small automaton. What we have is a very big non-deterministic automaton, and determinizing it is also a big operation. So we would want to construct an explicit small automaton for the alternating normal form. That would be nice. So what we're going to do for this is find another characterization of the alternating normal form, because the one we have for now, with the left needing to read all the rest of a word, doesn't really go well with having an automaton that can only read from left to right. So that's what we're going to do. Is that okay for now, or is there any questions? Okay. So I'm going to talk about a local characterization for the alternating normal form, which is the main thing we proved with Vincent. So for that, there's a little game, which is which of these 2 word is in alternating normal form. So I already gave a possible decomposition. you can see that there is only one letter difference here that has been moved up between V and W. So let's look at it. V first, there's this kind of pattern here, which I will call a stair, something like that, a staircase. So this is a sequence, a factor of sigma 1, sigma 2, sigma 3, and so on. And this little pattern has the property to be very commutative, meaning that it commutes with most of the other letters. In practice, those two blocks can be pretty much commuted. And this will cause problem because now we can take the bottom of the stairs and put it at the left. And we found another representative of V that has a bigger first block, which contradicts the fact that V was in alternating normal form. Okay. Let's look at W now. W has also this pattern, but here what saves it is that it has a similar pattern here in its previous block. So here we have a subword that goes from sigma 2, sigma 3 to sigma 4, which is of the same length as the pattern here. And it just so happens that this is able to stop, to block this from going through to the left. So you need to manipulate it a bit to see that it works, but as long as the second block of W has this subword, this factor cannot go through. And this is actually a necessary and sufficient condition, which means that at the end of the day, W will be in alternating normal form if and only if it has a decomposition for which every block is in alternating normal form. And if one of the blocks begins with such a staircase, then the block before must have this pattern. Yeah. For the beginning of this block, this is a factor that we need to have. This pattern needs to be a factor, but for the block before, it's only a subword that we need. So there's a bit of work to see that those are invariants of the braid and everything. There's a lot of things hidden here, but here we need a subword, which is easy to check when reading with an automaton. And here we need a factor, which is also easy to check. Okay, is that good with everyone? Nice. Okay, so now that we have this, we'll be able to construct the minimal automaton. A little side note here is that the first block is annoying in the sense that it's different from every other block because it doesn't need to start with a specific letter. Every other block needs to start with the top or the bottommost letter, whereas this one can do everything it wants. And also it's completely independent of the rest, meaning that the word is in normal form if and only if the first block is in normal form and the rest is in normal form. So when constructing the automaton, we're only going to construct the automaton for words which don't have a first block, and then we will go back to the general case. We can go back to the general case later. Okay, so this is why we only look at words which begin with sigma n. Okay, so we can start with n equals 3. So this was already known before the characterization because it's a very small case. Here you see it's the same automaton as before, but without the little start here. We need to start with a sigma 2 here. And from this will be our building block to construct the next step, which is a bit bigger. But we're gonna take a bit to understand what all of this corresponds to. You can already see that there is 4 copies of the previous automaton and some other states here, some bonus states whose usefulness will be explained later. So for this, I'm gonna do a small walk in the automaton with a word that is indeed in alternating normal form. So as I said, I ignore the first block. And here we begin on this state. Why? Because the left part will correspond to odd blocks, so blocks that don't use the bottom strand, and the right part will correspond to blocks that don't use the top strand. You can see that to the left there is no sigma 1, and to the right there is no sigma 3. Okay, so first thing we can observe. At first, we just move into pretty much a copy of A3, but at some point we're gonna change block here. So this corresponds to the fact that we've seen this little pattern here, the subword we are looking for. So on this block, we have not yet seen the sigma 2, sigma 3 subworld. And on the bottom block, we have seen this subworld. Okay, so we just have 2 copies just to remember 1 bit of information. So that's life. Then we can just continue going through the previous automaton. And at some point, we change side. When we change side, we need to check that the factor at the beginning is not too long. Because if it's too long, it will be able to pass through. So this is why this is what those states are for. They are for checking that we don't do anything strange here. And when we have finished reading the stair and everything is okay, we can go back to a more usual state. So this construction works for all n, and is very explicit, and actually we directly get the minimal automaton by constructing it that way. So we can show that what we get is actually the minimal automaton for recognizing this language. Moreover, we can compute the number of states pretty precisely. There's no problem here. And we can see that it's in 4 to the n, which the intuition is pretty reasonable because we have 4 blocks at each time, and the rest is pretty much negligible. Okay. And we have also precisely the number of transition, a bit trickier, but it's okay. Not much of a problem. And we get n to 4 to the n. Okay. So this is the 2 main things we've got, the characterization and the minimal automaton. So what can we do from now? There's a lot of things we can do afterward. First, I briefly mentioned the automaticity, and this is actually what I'm working on right now. This is reduction in progress. There's also the rotating normal form in the dual monoid. So this is a very close cousin to what we've done right now, a closed monoid with a very similar normal form that has been studied by Jean Fromentin in 2000 in his PhD thesis from quite some time. And I have strengthened the results somewhat, so I'm also writing up this. And the fact that we have similar results in 2 different monoids makes me want to find a generalization that would work in a bigger context. So I've talked about this with Jean, and we're working on it right now. And there are 3 other things I did not tackle yet, which are random generation, which has been done in the context of the lexicographic normal form, because from the automaton, we can do random generation of braids. It has also linked with the ordering on braids, but I'm not gonna really go into this right now. And also, I've only worked in the monoid, so I did not have any inverses, which was nice because every representative had the same length. In the group, everything is much more nasty, and there is not really any nice normal form here. So this could be something to look at afterwards, seeing if we can generalize this also for groups. Thank you very much.
Thanks a lot. Questions for June? Yes, first.
Given the normal form,
Yeah.
Sorry, can you say something about the number of non-normal form, the number of representant?
The number of what?
Of representation of the braid. At the beginning, you show an example with beta,
Yeah.
which has 4 representation, representation, and can you compute the number of the size of the equivalence classes?
Yeah. Well, I know we know the number of words. This is no problem. We also know the number of braids of length fixed. This is already known way before this. But if we take a single braid and we want to compute the number of representative, I don't know. I don't know if this will help because we just want to pick one representative. So it's unclear that this is a way to get these results. But yeah, that's one way we could go.
Thank you.
Yeah, I was looking at the generators for the braid group. It looks very similar to those for the symmetric group.
Yeah.
Except for the relation SI squared equals 1.
Yes.
So for the symmetric group, I mean, we can establish the normal form and also conormal form via bubble sort through transpositions. Are there some similarities? with
Yes,
those?
yeah, very good question. We actually have an explicit algorithm to go from any word to the alternating normal form. That is exactly as you said, pretty much a bubble sort where we just do little flips until it converges. So it goes in like the complexity is in n squared times L, with L the number of, yes, n squared times n, we have n the length and L the number of strands. So this is pretty okay. And this is linked to the property of automaticity that I didn't explain, but automaticity gives a very fast way to compute braids by just switching doing some bubble sort thing. Also, you said that it was closely linked to the symmetric group, and this is true. We can also do braid groups associated to other Coxeter groups, not only the A type. And this is actually what we are going to do with Jean-François Martin when we're going to generalize. It's trying to look at other braid groups, not on the symmetric groups, but over the B type and so on. Yeah. So, yeah.
Other questions?
So this is a naive question, but is there any good reason to choose this alternating normal form?
Yes, this is this part here. At first, it was introduced by Patrick Deharnois and Jean, well, yeah, by Patrick Deharnois some times ago, because there is a canonical way to order braids, which has a very convoluted definition, and it's really hard to see even that it's a total order. But it coincides with the order of braids given by the lexicographic order on alternating normal forms. So we first compare the number of blocks, and if the number of blocks is equal, we compare each block. And those two orders coincides, which means that if we have more information on the alternating normal form and the blocks and how it behaves, we can deduce things on the ordering of braids, which is another big subject in this domain. So this is where it was coming from initially. This is why it emerged, compared to the lexicographic normal form, which is not just very natural and there's not really any motivation behind it. This.
More questions? No? Then thanks again for the talk.